Okay, let's get started. The next parameter we're going to discover is the rest angle scale. With this simple geometry, it is very easy to demonstrate its essence. Let's play and see what we have by default. So, I want to increase the bend stiffness to keep its shape during simulation. That's better. Now let's talk about the rest angle scale. The rest angle of the bend constraints will be the original dihedral angle between the triangles. This scale can be used to increase or decrease this. Setting to 0, we'll treat the original configuration as a flat sheet. Let's check. As you can see, all starting angles are straightened. It turns out that, if we put 0.5, then exactly half of the initial angles will remain. Conversely, if we set the values above 1, then the angles will become even sharper. Like now. That is, exactly the opposite happened. Well, since the resolution of this geometry is very low, we can change this parameter in real time inside the dot network and see how it reacts. For that we will again use the Vellum constraint properties node. Connect to force output, then specify bend constraint. Now let's activate the rest length scale just to change it during simulation, but before we start tweaking it in real time, let's pin viewport at SOP level. So, we can already play the simulation and start to change the rest angle scale. See how the degrees of the angles change depending on rest angle scale value, and since we have a low resolution we can do it in real time. Okay, that's all I wanted to show you in this example. Now I suggest switching to another scene where I prepared another example file related to the rest angle scale. So this time we will use this geometry, which has a little noise on it, that will provide the initial rest angle. Now let's check what we have by default. As expected, it falls under the influence of gravity. Now I propose to pin the upper corners so that it hangs. Well, on properties of the Vellum constraint, there is a section dedicated to pinning points. Later we will go into detail about all types of pin and what happens under the hood, but for now it is enough to know how to pin the specified points. Just click on this icon, then select the points you want to pin and press enter. Look, here are the numbers of the points that we have pinned. Now let's play and see what we got. Good, it's already hanging from the pinned points. The only thing that I do not like is that it swings up and down for a long time, which doesn't look good. Now I'll show you how you can get rid of this swinging effect. Let's switch to the Advanced tab, then change the integration to first order. So, let's see what is changed. As you can see, the first order damped all excess energy in the system, but this is not always good. There are times when on the contrary you need to maintain more energy in the system. The default is second order, but in any case, if collisions are detected the system will fall back to first order to avoid excessive bouncing. In addition, there is another option for dampening excess energy. It is a velocity damping, which is a brute force approach to reducing dynamic velocity. The velocity is scaled directly by this amount, causing sudden movements to be quickly damped. Let's put some small value and check the result. As you notice, the swing faded quickly. If you increase it further, the velocity will decay much faster. Well, now let's get back to the rest angle scale. Before touching it, increase the bend stiffness. Then reset to 0 the rest angle scale and see what we get. As expected, all wrinkles disappeared and it became flat. Okay, now let's increase the rest angle scale and check again. See, the wrinkles become more visible. Let's keep on increasing it and watch how it changes. You see, they became much more aggressive, but I think we can crumple it up a bit more. Let's try a 10. See, artifacts have already begun due to self-collision. So to summarize, we can say that the rest angle scale is a good way to exaggerate existing angles or reduce them. Now I want to very quickly show another interesting example, again related to the rest angle scale, then we will move on to the next parameter. Okay, in this example, I animate the rest angle scale to untwist this geometry and then scroll it back. So let's see the result. Well, now I'll show you how I did it, and then we can move on. In Constraint properties, I only increase the bend stiffness, then add 5 substeps to make it even stiffer. Finally, I animated the rest angle scale using the Vellum Constraint properties node inside the DOP network. Look, at the beginning the rest angle scale equal to 1, then gradually goes to 0, remains 0 for a while, and at the end it increases to 2.5. That's all I did, so simple. Okay, now let's move on to the next parameter of bend constraint. For this I have prepared some good examples, let's switch there. Well, the next parameter is the stiffness drop-off. For that I have prepared this simple example, the tube falls to the ground, all vellum settings by default. Now let's increase the stiffness decently so that the tube retains its basic shape. Good, now let's talk about the stiffness drop-off. With this parameter, you can specify the number of degrees away from the rest angle at which the stiffness of the constraint decreases to 0 or increases from 0 to full stiffness, depending on the direction of the drop-off. A decreasing drop-off means that the stiffness starts at full strength and decreases to 0 at the drop-off degrees from the rest angle. An increasing drop-off means the stiffness starts at 0 and increases to full stiffness at the specified degrees away from rest angle. Well, let's start with the decreasing mode. Set 10 for stiffness drop-off, then check the result. See, where the angle of deviation from the rest angle exceeds 10 degrees, there the stiffness became 0, but where it is not exceeded, there is still a high stiffness. Therefore such sharp creases have transformed, and due to them the geometry collapses. Now let's increase the stiffness drop-off and check again. Look, it has become less broken than in the previous one. Only angles reaching 15 degrees or more received 0 stiffness, therefore it didn't collapse completely to the floor. Let's visualize the bend angle and look again. Adjust a maximum bend angle, then check how it looks. See, where it is marked in red, there the deviation angle is greater or equal to 15 degrees, which means that there is 0 stiffness, that's why sharp creases were transformed there. Okay, now let's disable the visualization, then continue to increase the stiffness drop-off and see how it affects the simulation. As you can see now we have much less creases. Let's keep increasing the stiffness drop-off until they won't be transformed at all. Fewer and fewer broken corners, I think if we increase it a little more, then it won't be at all. Let's put a 25 and have a look. Now the deviation angles do not reach 25 degrees, which means that we do not have 0 stiffness anywhere, so we don't have broken corners. We also have a parameter to specify the minimum stiffness instead of 0. For now let's turn it off, then reduce the stiffness drop-off to 10 and see how it looks, then we can specify the min stiffness and compare. Well, the result looks like this. Now let's turn on the min stiffness, then put a small value and check the result. See, it does not completely lie on the floor, since broken corners have stiffness equal to 0.05. Let's slightly reduce the min stiffness and look again. See, now the min stiffness is barely enough to not completely lie on the floor. Well, this is all that I wanted to show with this example. Now I propose to switch to another example file where we will continue to explore the stiffness drop-off and other circumstances. So, this time we are going to use this simple example. The cloth falls on the collision geometry, all vellum settings by default. Now let's increase the bend stiffness decently and look again. See, all small folds have disappeared, only we have large round folds. High stiffness value does not allow them to transform. Now let's turn on the stiffness drop-off, then select the decreasing mode, set it to 7, and check again. Notice how everything has changed dramatically. Now we have a fairly stiff material, but at the same time sharp folds have been transformed. Well, let's increase the stiffness drop-off further and look again. As you can see, most of the creases have gone because the bend angle did not reach the value we specified and the stiffness did not decrease enough. Let's continue to increase the stiffness drop-off even more and see again. Now we have almost no sharp creases, but still stiffness drop-off has a noticeable effect. To see how much the stiffness drop-off affected the simulation in this case, I suggest turning it off, then running the simulation again, and comparing the result. In general, the result is similar, but on the other hand there is a noticeable difference. There is no roughness in the folds. Good, this is all that I plan to show with this example. Now I propose to switch to another example, where we will already consider the stiffness drop-off in the increasing mode. Okay, this time we will use this geometry, all vellum settings by default. Now I want to pin the lower points so that I can then increase the bend stiffness and hold it in place. Press space 3 combination just to switch front view, then select the bottom point and hit enter. Let's also visualize the pinned points. For that, go to the Visualize tab, then turn on Pin to Target checkbox. Take a look, pinned points are marked in the form of spheres. You also can adjust their radius. Or you can change their color. Okay, now let's start the animation and see what we have. So, due to low stiffness, the geometry does not hold its shape and falls down. Okay, to prevent falls, let's increase the bend stiffness. That's better, now the stiffness is enough to keep it in shape. Good, now I want to add turbulent wind to make it wiggle. For that, let's dive into dot network. Then, I will create a pop wind. Connect to force output, then start adjusting wind properties. Put 5 for noise amplitude. 0.5 for swirl size. Then increase a little roughness. Let's also slightly increase the turbulence iteration number. And finally, I want to add directional wind along the positive y-axis. That's it, let's see what we got. Well, it wiggles under the influence of a turbulent wind. Now it's time to play with the stiffness drop-off and see what happens. Let me remind you that this time we will use it in increasing mode. So let's start at 20 degrees and see how it looks. See, the basic behavior did not change much, but since closer to the rest angle the stiffness is 0, this contributes to the appearance additional small wiggles without losing the main shape. Let's continue to increase the stiffness drop-off and see how this affects the simulation. It became much weaker closer to the rest state, that's why the wind wiggled it so easily, but main shape doesn't change much. Let's also set the maximum value and check how it looks. Now it gets stiffer, only a decent deviation from the angle of rest, that's why it is so strongly affected by the wind. Well, in this example I've shown everything I wanted, now let's move on to another scene where we'll look at a different situation where the stiffness drop-off in the increasing mode can add a lot of detail to the simulation. This time we will use this torus. So far everything is by default. First, let's increase the bend stiffness so that it retains its shape. Well, now the stiffness completely suits me, but at the same time I want to make it even more jiggling than it is now, and this can be done with the stiffness drop-off in the increasing mode. So, let's put 20 and see what will change. Take a look, now we already have a lot of jiggling because the stiffness starts at 0 and after bending 20 degrees, reaches the value we set. To make it much more noticeable, let's increase the stiffness drop-off even further and look again. Obviously became much weaker, up to a deviation from the rest angle by 50 degrees. Okay, now let's set the maximum value and see how it looks. As you can see, the stiffness has decreased again, but at the same time, the shape as a whole remains. If you need to add a little bit of jiggling effect, but at the same time, the main dynamics remain the same, just set a small stiffness drop-off. So, that's all I wanted to show in this lesson. In the next lesson we are going to discover the plasticity properties of the bend constraint. See you in the next lesson.